Hello guys, hope you all are doing well. So in the continuation of the previous lecture series based on GATE, we were solving the GATE questions, uh, previous year GATE questions, and we were solving 1990s GATE questions. So today we have a new question. So without wasting time, uh, we will start solving a new GATE question. And this time we will solve for process calculation. Solve right here. Okay. 1990 GATE section B. Process calculation. Okay. So what question is saying? The question is saying the question will be visible to your screen. Pure propane C3H8 is burnt in an excess air in the following analysis of combustion product in volume percentage. Calculate the percentage of excess air. सबसे पहले प्योर प्रोपेन जो है दैट इज C3H8 is burning in presence of air. ठीक है, burning and the final gas composition or product gas composition. We have CO2 5%, CO 3.5%, H2O 11.4%, 7%, and 73.1%. Okay. Now we have to choose a value of the exit gas, final gas, because the composition given for the final gas. Suppose if I'll take let 100 kilomole of product gas, or I can choose anything 150, 200, anything kilomole or mole is depending on K is just a number, that is 1000. That's it. Okay. So why I choose 100? Because this total will become 100. So if I want to find the quantity of CO2, then it is 0.05 into 100 equal to 5, 5 kilo. So for simplicity, I have chosen 100. I can choose 150. I can choose 200. So according to that, if I will choose 150 kilomole out, output gas, flue gas, then CO2 quantity will change. 0.05 into 150, that is something big. Okay, so I choose 100. So here basis 100 kilomole of product gas. Okay, so CO2 5 kilomole, CO 3.5 kilomole. Okay, now the question is saying calculate the percentage excess air. So very first we write the formula. Percentage excess air is equal to air totally fed minus theoretically required upon theoretically. Theoretically required air is the air, I can say like that, that theoretical air required or theoretical O2 required is that air which is consumed by the main reaction. Which is consumed by the main reaction. You will understand it later. Uh, I'll tell you. So C3H8 is burning. C3H8. C3H8. So here write the reaction C3H8 plus in the presence of air, and always remember air contain only O2 plus N2, nothing else. It contains, but we will consider only these two because these are in major quantity. So C3H8 plus O2, that gives CO2 plus H2. We'll balance it later. C3H8 plus O2, that gives CO plus H2. So H is 8, so 4, 4. C is 3, so 3, 3. Now 3 to just 6. 6 plus 4, 10. So here 5 and here is 7. Okay, now the equation is now. Theoretical O2 is that O2 which only comes from the main reaction, corresponding to the total reactant consumed. That means theoretical O2 is O2 required by main reaction over complete combustion of reactant. Okay, so here reactant is C3H8, which contributes to both the equation. So we will calculate how much quantity of C3H8 reacted totally. Then corresponding to this value, how many moles O2 required. We will not consider this. Okay, this is undesired reaction or side reaction. Okay, now we have N2 is equal to 73.1%, and we know that air contain O2 plus N2 in the 21%, 79% percentage. Okay, so suppose the quantity of air fed in the system, air fed totally, let X, which is equal to 73.1 upon 0.79, because if air fed X, then 0.79X will become 73.1, right? This is the only N2, because N2 is an inert component. It will never react with any of the product or reactant. So whatever the quantity we have in the input, the same quantity will get in output for the inert component, right? So from here we will get air fed X is equal to 92.53 kilo. This is it. Okay, now this is air fed. One thing we have calculated, air fed totally. Now theoretical air required. So for theoretical air required, first we have to calculate how much C3H8 has been reacted. So C3H8 totally reacted is equal to, since we are finding C3H8, so its stoichiometric coefficient should be the numerator. So 1 divided by 3. This is the stoichiometric coefficient of CO2 into quantity of CO2, that is 5 in the first reaction. From reaction first, plus in the second reaction 1 is the stoichiometric coefficient of C3H8 divided by 3 stoichiometric coefficient of CO into 3.5 quantity of CO, kilomole. This should be kilomole. Okay, by reaction 2. So totally it will react of around 2.83 kilomole. Okay, let's check once. 2.83 kilomole. Okay, now this is the quantity of C3H8 which reacts totally in both the reactions. So corresponding to this quantity, how much oxygen has been reacted based on the desired reaction. So our desired reaction is first reaction. So based on the first reaction, O2 theoretical required. Theoretical always comes from the equation. O2 theoretical required will be equal to 5. We are finding O2, so its stoichiometric coefficient will be the numerator. 5 divided by 1 is the stoichiometric coefficient of C3H8 into totally reacted. That is 2.83 is the totally reacted kilomole. So it will come 5 into 2.83, 14.15. 14.15. This is kilomole. Theoretical O2 required, but we have to find the theoretical air required. So just divide this quantity 14.15, which we have calculated just now, divided by 0.21. Okay, divided by 0.21. 0.21 because air contains 21% of oxygen, 67.3. So this is theoretical air, 67.38 kilomole. Now just put all the values in the formula. What is the formula? Percentage excess air is equal to O2 fed totally. Sorry, air fed total. Percentage excess air. Air fed totally, that is 92.53 minus theoretical O2 required, theoretical air required, sorry, theoretical air required 67.38 divided by 67.38, or the same answer will come if we will calculate on the basis of O2. Percentage excess O2 and percentage excess air will be same. O2 totally fed, how much? Totally fed will come from this, from where? From there. How much? This is the total air, so quantity of O2 will be 0.21 into 92.53 kilomole. So this will become 19.43 minus O2 theoretical required. O2 theoretical required. This is we have just found just now 14.15 upon. Both the things will give the same answer. Okay, let us check. So 92.53 minus 67.38 divided by 67.38. 37.3. 37.33%. And here, let us check whether we are doing right or not. 19.43 minus 14.15 divided by 14.15. 37.3. Right? 37.3%. Okay, so this is the concept of percentage excess required. The very common mistake which all the students do, what they did, what they do, they calculate the overall O2 required from the reaction, and that they named as theoretical O2. So most people, most students, they generally do a common mistake. That is, while calculating the theoretical O2, all know that theoretical O2 comes from the reactions. Okay, many students consider both the reactions, desired or undesired, but theoretical O2 always comes from the complete conversion of the reactant based on the main reaction. Okay, suppose C3H8 plus 5O2, that gives 3CO2, 4H2O, C3H8, 2O2, 3CO plus 4H2. So always remember, I can do this also for theoretical O2. Theoretical O2, I can do this also. What I know that C3H8 reacted from first reaction, C3H8 reacted from second reaction. I know that. So 5 by 1 into 5 is the stoichiometric coefficient of O2. 1 is the stoichiometric coefficient of C3H8. So C3H8 reacted by first 5 by 3 into 5 by 3 plus 3.5 by 1. 3.5 is the stoichiometric coefficient of this. 1 is this, and quantity, and C3H8 reacted by reaction to 3.5 by 3. 3.5 by 3. So this part is wrong. We will not consider this part for theoretical O2. Okay, theoretical O2 will calculate based on the complete conversion of the reactant correspond to the first reaction. This is the first reaction. Okay, we will not consider this. Okay, but we will consider the complete conversion. The reacted, totally reacted C3H8. Reacted C3H8 we will consider. And based on that, how much O2 will be required? That will give the theoretical O2. Okay, so this is one of the most important concept in the process calculation, and I think one of the most toughest. So if you have any doubt or any problem, just comment it below. Okay, I'll try to give the explanation, and thank you guys. Take care. Bye. Stay focused.